Hi and welcome to this section where I would like to look at a few more properties of the determinant. We start with saying that the determinant of a triangular matrix, is the product of its diagonal entries. Okay, so the determinant of a triangular matrix, okay, in a triangular matrix will take the form where all the entries below the diagonal, either below the main diagonal or below or above the diagonal are 0. In this case we can consider the case where all the entries below the diagonal are 0. Okay, these are not all, the ones above are not all 0, but then the ones below are all 0. Okay, so such a matrix here, we say that if you realize that your matrix is diagonal, then its determinant is simply going to be the product of the entries on the diagonal. Please note, again I emphasize that it could have been the other way around. It could have been of this form where we have the determinant and then we have maybe the entries here on the diagonal, okay, and then all above are 0, and then these are not all 0, okay, up to t n 1 and so on. Okay, still we would say that the determinant would simply be this product here. Okay, well, now what else do we have here? We would like to say that transposition does not alter determinants. Transposition does not alter determinants, i.e. the determinant of A transpose is the same as the determinant of A, okay, for all n by n matrices. And now we would like to look at effects of row operations. Okay, remember the elementary operations which we looked at? Okay, if you do remember them, well, for completeness sake we can just do a summary of them. We had okay, maybe let's start by saying that we'd like to start by saying that let B be the matrix, okay, obtained from A, okay, this n by n matrix A by one of the 3 elementary row operations we looked at. Okay, remember we had type 1 operation where we interchange, okay, any 2 rows. Maybe we interchange rows I and J, okay, J not in the sense of a column, J in the sense of a number. Okay, so we are saying interchange in 2 rows, maybe the first row and the second row, or the third and the fourth, something of that sort. And then we had type 2, and then what was type 2? We said type 2 is if we multiply any row, okay, by a non-zero scalar alpha. Okay, and then we also had type 3, which was where we added non-zero scalar, that is alpha, okay, times, okay, the multiple of, multiple of one row, that is alpha times row I, okay, then we added this to row J, okay. Those were the three elementary operations. So we'd like to look at the effect of these elementary operations on the determinant. So what are the effects? The effects are quite interesting here, okay. The effects are as follows. One, if we interchange any two rows, okay, then the determinant of the resulting matrix, that is after you've interchanged any two rows, that is, then we get the matrix B, then its determinant is going to be negative determinant of A, okay. When you interchange any two rows, then the new matrix is equal to get the determinant of the new matrix is equal to the determinant of the negative determinant of the original matrix, okay. And then if we multiplied any row by a non-zero scalar, okay, then the determinant of the new matrix, that is P, is simply going to be alpha times the determinant of A, okay. And then for type 3, we are going to say that the determinant of B here is going to be the same as the determinant of A. We are not going to have any change, okay. So those are the three elementary row operations, and those are the effects, okay, of these operations on the determinant. So what else do you want to look at? Okay, maybe just one or two more remarks here. We are going to say one or two more remarks about invertibility, i.e. if a matrix, a matrix which is invertible, it has the inverse exists, and the determinants, okay. So remember, we already said that we can obtain the inverse of the matrix by multiplying 1 over its determinant times the adjoint matrix here, or the adjugate, okay. So one important thing to note here is this determinant of A is not equal to 0, because division by 0 is not allowed here. So we say if the A n by n is non-singular, remember the term non-singular refers to a matrix which is invertible, okay. So this is invertible if and only if, okay, the determinant of A is not equal to 0. We don't go for the proof, but please, just a point of reference here is that whenever you see this word if and only if, that means that the proof is two-way. The proof is what? Two-way. It means that the determinant, if the determinant is, if a matrix is non-singular, it means that the determinant is not 0, and if the determinant is not 0, it also you can also prove that the matrix is non-singular. All right. Okay. So, or equivalently, we can say that this n by n matrix here is singular, i.e. the inverse does not exist, if and only if the determinant of A is 0. Again, the same explanation I've given above about proof which is two-way holds here. Okay, so thank you, and you can go through the rest of the the rest of the book in that chapter, and then if there is anything else which you think I need to talk about, you can please mention it, okay, in the comment section. So thank you, and we meet next time.